Laboratory testing is able to provide powerful data to select and compare the performance of materials for a variety of applications. To best understand the results, it is important to know what each test is measuring, the procedure that was used, and that the data was acquired using established and repeatable protocol. All test data measured by Parker is based on test methods from the American Society of Testing and Materials in our ISO 17025 accredited laboratories. The ultimate use for this data is to help customers decide which material will work best for their given application. Contemporary test results from Parker contain two main sections. First, the cover page provides a summary of the compound, also called material, as well as the purpose of the test, and the application recommendations for temperature and fluids. The second section of the test report is the laboratory-generated data, which provides numerical results and a thorough description of the parameters for each test performed. The basic types of testing covered in this section are often original physical properties, compression set, heat age, fluid immersion, and low temperature testing. It is important to note that testing can be completed on either suitably sized O-rings or on test slabs. When comparing two different test reports, it is important to observe if the specimen, test methods, and conditions are the same. If not the same, the comparison is indirect and may not be a fair assessment of the results. The first test results listed in the report data are the physical properties: hardness, tensile strength, elongation, and modulus. Hardness, also called durometer, is a measure of surface deformation due to a specified load. Parker O-ring materials are specified using the Shore-A hardness scale as measured by a durometer. The Shore-A test is conducted by applying a force axially from the indenter to the O-ring or specimen surface. Results of the Shore-A test are given on a scale of 0 to 100, with 100 being the hardest. The majority of O-ring materials are between 70 and 90 Shore-A, but can be as soft as 40 or as hard as 95. When specifying a Parker material, the numbers after the hyphen indicate the hardness of the material in terms of Shore-A scale. In this example, the nitrile O-ring has a Shore-A hardness of 70. The tolerance on hardness is generally plus or minus 5. The test method for measuring Shore-A hardness is ASTM D2240. There are also other scales for hardness such as IRHD and Shore-M. While similar, there is no direct conversion between different hardness scales. Applications with pressures above 1500 psi typically need an O-ring material with a higher durometer, such as 90 or 95. Tensile strength, ultimate elongation, and modulus are measured at the same time and can be measured on either O-rings or test platens. Test platens are slabs of rubber 75 thousandths of an inch thick from which an ASTM D412 Die C specimen is cut. The Die C specimen are often referred to as dumbbells or dog bones. Testing of platens requires the ends of the dumbbell to be clamped into the tensometer and pulled at a controlled rate until the specimen breaks. ASTM D1414 requires O-ring testing to loop the specimen over the spools, which are pulled until the O-ring breaks. Tensile strength is the maximum stress achieved before failure, and this value is reached at the maximum elongation value. Ultimate elongation is the percent change from the original length to the length at failure. Modulus is the stress at a specified elongation, typically 100%, which is double the original length. Elongation is more relevant during the installation of O-rings than in the direct and intended application. As an example, consider an O-ring that must be stretched over a piston or other fixture in order to seat in a groove on the shaft. If the O-ring is elongated beyond its limits, the O-ring can break. High tensile strength, ultimate elongation, and 100% modulus can contribute to an elastomer's toughness, which is an important property in dynamic applications. A very important test for elastomers is compression set, because it is the most common failure mode in O-ring applications. Compression set is defined as the loss of thickness after prolonged compression, also called squeeze. Per ASTM D395, Method B, the O-ring or specimen is compressed between plates, and spacers are used to ensure the compression is 25% of the O-ring's original thickness. The block is then placed in an oven for a period of time such as 22 or 70 hours. Specimens are removed from the blocks and cooled. The specimen thickness is measured to see how well it returned back to its original shape. The lower the compression set percentage, the better, because it indicates that the compound rebounded, whereas a compression set of 100% indicates that the compound did not rebound at all. In an application, leakage would be expected at approximately 80% compression set. Heat aging is another method for comparing differing O-ring materials and can be performed on O-rings or test platens. Heat aging refers to the change of physical properties when compounds are exposed to temperatures at or above the upper operating limit for the compound. Elevated heat can cause chemical changes in any compound, and this test is a way to identify the impact of that heat. Heat aging is performed by taking either O-rings or platens and placing them in an oven or heated chamber for a planned time and temperature, based on the known limitations of the elastomer family. After heat aging, when the samples come out of the oven and are cooled, the physical properties such as hardness, tensile strength, and ultimate elongation are measured. The values are compared to the original physical properties and reported as the amount of change. The change in Shore A hardness is listed as the points difference, while the tensile strength and ultimate elongation are reported as the percentage of change. Applying the heat age data from a test report to an application will vary, but a good starting point is that if a compound experiences a 10-point difference in Shore A hardness or loses more than 50% of its tensile strength, there may be a better material. Fluid immersion is one of the primary concerns of O-ring application and is the subject of many lab tests. When the O-ring is installed in an application, it will be sealing a fluid, and we need to be sure the fluid and O-ring material are compatible. If incompatible, the main problems will be swelling and shrinkage. Swelling could lead to shortened seal life, and O-ring shrinkage could cause leaking and a chemical reaction that results in O-ring degradation. The fluid immersion test can be between any fluid and O-ring material, and the specimen can be O-rings tested per ASTM D1414 or platens per ASTM D471. The specimen are placed on a wire and immersed in the fluid in a test tube or beaker. The fluid and sample are placed in a heated block or oven and left at temperature for a predetermined amount of time. At the end of the test, the samples are removed and cooled in the same fluid. Once cooled, the physical properties and/or volume is measured and compared to the values of the unaged specimen to determine the amount of change. The change in Shore A hardness is listed as the points difference, while the tensile strength, ultimate elongation, and volume are reported as the percentage of change. Swelling is the most common indication of fluid incompatibility and occurs when the surrounding fluid is absorbed into the O-ring compound. This causes an increase in the volume of the O-ring and can lead to problems in the application. Applying the fluid immersion data from a test report to an application will vary, but a good starting point is that if a material's swell is less than 20% of the original volume, the O-ring is compatible in both static and dynamic applications. When swell is greater than 20% but less than 40%, the O-ring is recommended just for static applications, and when the swell is greater than 40%, the O-ring is not recommended for any application. Shown in this example, we see that one O-ring is unchanged, meaning the material is compatible, while the other has swelled greatly, indicating it is not compatible with the fluid. Low temperature testing is imperative to ensuring sufficient seal performance in industries where low temperature operating conditions are common. Low temperature causes an increase in brittleness of the compound, which leads to cracking, breaking, and failure of the O-ring. There are multiple methods for testing, including ASTM D2137, crack resistance, and ASTM D3418, glass transition. Parker tests compounds at low temperatures using ASTM D1329, also called the TR10 method. TR10 is a temperature at which the compound loses resiliency and transitions from rubber behavior to soft plastic behavior. In this method, the compound is clamped, then stretched 50% in a temperature-controlled chamber, and frozen to a temperature below what the material can recover from. At this point, one end of the specimen is unclamped, and because the temperature is colder than the material's flexibility, the specimen stays elongated. Gradually, the chamber temperature is increased, and when the material regains flexibility, it begins to retract. The temperature at which the specimen retracts 10% of its elongated length is defined as the TR10 temperature. The O-ring industry defines a material's low temperature rating by taking the TR10 measurement in Fahrenheit and subtracting 10 to 15 degrees. Application experience has proven that an O-ring elastomer will seal statically 10 to 15 degrees below the TR10 temperature. O-rings perform well at and above the TR10 temperature in dynamic applications. When reviewing lab results, always check the time, temperature, and test methods utilized in the testing. ASTM, JIS, DIN, or ISO procedures should also be followed to allow for repeatability and consistency across all tests. In addition, the facility should be an ISO 17025 certified laboratory. Lastly, it is important to not solely rely on laboratory test results. Actual performance testing should be completed in real-world performance conditions before full-scale implementation of an O-ring. For more information, or to download a material test report, please visit www.parkerorings.com and check out Mobile Inform.